This is a talk about simultaneous search problems. These are a very broad class of decision problems. But my motivation comes from college admissions markets. And in college admissions markets, we often observe that students are advised to apply to a diverse portfolio of schools. So some rich, match, and safety schools. And empirically, it's observed that when application costs go down, students expand their application portfolios both upward and downward, applying to more selective and to less selective schools. Now, these practices of diversification are ubiquitous, but they are inconsistent with the standard analysis that we use in economics, both for theoretical models and for applied studies. In these models, Chad and Smith show that applying to safety school should be ruled out, and that when application costs are reduced, optimal portfolio should expand only in an upward direction. In this paper, I present a generalized framework to think about simultaneous search problems, which nests the Chad and Smith or the standard environment, but has more, but generalizes to other environments as well. And I show that the results emphasized by Chad and Smith actually emerge because of the common assumption that admissions decisions in each college are independent, or at least independent, conditional on the information that's available for the applicant. What I mean by that is not that the models rule out the possibility that Itai is a stronger applicant than I am, and so his chances are higher in every college. That's okay. What is ruled out is the possibility that if I apply to Harvard and to MIT, and I learned that my application to Harvard was rejected, I can update and learn something about my chances to get into MIT. So that's what the standard models rule out. That's what I'm going to allow today. And what I'm going to show you is that when you allow for a high degree of correlation in admission decisions, the predictions that I emphasized in the first slide actually emerge. I'll also show you an algorithm for computing in many environments. I'll touch upon one application today, the optimal portfolio. That's useful for applied work, like some people in this room are working on. And I'll derive a bunch of other comparative statics, which include the fact that students with stronger outside option, like access to another admission process, apply more aggressively. Students who are more risk-averse apply less aggressively, and students who are more optimistic about their admission chances apply more aggressively. So to summarize the main contribution and the thing I'm going to focus on today, you can look at this picture, and the one that's closest to me summarizes what previous literature has found, Chad and Smith, Vora and Olszewski. What they show is that when admission chances are independent, optimal portfolios of larger sizes nest optimal portfolios of smaller sizes. So when you move from the optimal portfolio of size 1 to the optimal portfolio of 2 schools, the optimal 1 school is included in this portfolio. And this portfolio expands only upwards, so to more selective or more desirable schools. What I'm going to show you today is the second part of this picture. And what we see is that when admissions decisions are perfectly aligned, they are based on a single index, like an exam score, which you don't know. When you apply, optimal portfolios actually expand in both directions, and they refine one another as they become larger. Because the motivation comes from correlation in admission prospects, it's maybe worthwhile to stop for a minute and think when should we expect to observe such correlation. And one natural case is that of school choice, where we use single tie-breaking. Okay, so there are places where just by definition, admission chances are highly correlated. If we think outside of these environments, there are many common application processes where an exam is going to determine whether you get in or not, a single exam in all schools. And when you apply, you don't know how you fared in the exam. So in fact, most of the uncertainty that students are facing is not about the cutoff that Oxford is going to have. Those things are pretty stable. The majority of uncertainty comes from how will I perform on the exam. And going beyond these centralized or centrally designed situations, you can have highly correlated uncertainty if you think that there are common factors that are affecting schools' admissions decisions, and you just don't know how you stack relative to others. And leaving the domain of school choice and college admissions just one time, I won't do it again, simultaneous search problems are actually quite common in reality. You apply to multiple jobs at the same time, or companies try to sell to multiple consumers at the same time. And over there, you can also expect correlation in many environments. So it could be that I submit my paper to AER and Econometrica, and once both of them reject me, I should learn something and not try again in a top journal, but update what I'm doing. So this is kind of the idea that I'm going to talk about today. To fix ideas, I'm going to talk only about students applying to colleges. Okay? So I'd like to start with an example that illustrates how students should reason about applying to schools when admission prospects are correlated, and the pitfalls or the problems that analysts are going to face when they ignore this correlation. So imagine a simple town with two neighborhoods, east and west, and neighborhoods are perfectly symmetric, so there is half of the mass of the students living in each neighborhood, and each neighborhood has a good school and a bad school. The good school has only a mass quarter of seats, so it has fewer seats than students in that neighborhood, and an unconstrained bad school. Students can only apply to two schools. Equivalently, there is an application cost. And their admissions will be determined based on a lottery number that the city will draw randomly, which they don't know at the time of application, like in New York. And there is no neighborhood priority or anything. That's the only thing that matters is your lottery number. Why did I tell you that there are neighborhoods? Because students' preferences depend on where they live. What students want is not to have a big commute, so they prefer a local school, and they prefer a good school. But I'm not going to tell you which one is more important. So here's a summary of the previous slide. And now I claim that in equilibrium in this market, students are only going to apply to local schools. So they'll apply to both of the schools in their neighborhood. And the reason is that by symmetry, you either get into both good schools or to none. Each good school will require that you get a lottery number higher than 1/2. So you know that if you apply to both, you get into either both or none. You're better off applying just to the one you like most, the one in your neighborhood, and using your second application as safety. Okay? So what students should do is to apply to both good schools in their neighborhood. Now imagine an econometrician or an analyst who is misspecified. He perfectly understands what's going on. So he understands the functional form, and he understands that the game is common knowledge and everything. He just does not understand one thing. He does not understand that schools draw from a single lottery. He thinks that admission chances are independent. This analyst must deduce the following inequality. He must deduce that the expected utility from the portfolio that people actually choose is greater or equal than what he perceives to be the expected utility from applying to both good schools. Now, this is a mistake, because in reality, what's going on here is with probability half, you go to the good local school, and with probability half, you get rejected, but with probability half, you get into the other good school. In reality, this number is 0. But he doesn't understand that, so he's going to cancel out these two terms, and he's going to deduce that 2 beta is greater than gamma. Now remember, I made no assumptions about the values of beta and gamma, but this econometrician just deduced that quality cannot be much more important than proximity. So the policy implication or the policy recommendation that this econometrician is going to give, if he's using this model for estimation, by definition has to be that you shouldn't care too much about opening good schools. Okay? So here's the general framework of the paper. We're going to have a finite, or infinite actually, set of schools, alternatives, options. And students are going to have to apply to a subset of these schools. Maybe they're constrained or there are some application costs. They're not going to generally apply to all of them. And students are assumed to be small in the sense that they don't think about how they're changing the equilibrium or how their first choice affects the probability to get into the third choice. They know their utility from going to each school. So they know that they like Harvard more than Yale. What they do not know is whether Yale or whether Harvard is going to accept their application. So they face uncertainty about the realization of their application. The main innovation that I'm going to present is that the event in which I'm accepted to school I is not necessarily independent of the event that I'm accepted to school J. So to summarize, the optimization problem I'm going to face as an applicant is to maximize the one school, the utility from the one school I can attend. I can't attend multiple schools. And it has to be that I apply to this school, and it has to be that this school accepted me, and there are application costs which depend on the number of schools you apply to. And the key insight in this project is that if I apply to Harvard and to Yale, and I actually prefer Harvard to Yale, I'm never going to go to Yale if Harvard accepts me. And so my second choice school must be selected conditional on the information that is entailed by being rejected from my first school. So maybe if Harvard rejected me, Yale is not such an amazing selection. I should understand that maybe I'm not Ivy material, and maybe I should, use my second application for something more realistic. Okay? Now, what the literature typically did is assume that this has no information. Their decisions are independent, so being rejected from Harvard told me nothing about what's going to happen in Yale. Okay? Here is a slide I'm going to skip and just tell you that if you can solve a problem with dynamic programming, you can solve it with dynamic programming. This is a tautological proposition that basically says because this problem has a downward structure, I can solve it backwards. Okay? So I believe that people can figure it out. So to summarize, admissions, so now I'll give you the main application that I'll cover today. Admissions are determined based on a single index. There is going to be just one exam that determines everything. Each school is going to have their own cutoff. So more selective schools will have higher cutoffs. Less selective schools will have lower cutoffs. And it's going to be the case that I get utility UI from attending school I if I applied to school I passed the cutoff, so I got admitted to school I, and I didn't apply and get in to another school that I like more. Okay, so that's when I'm going to attend school I. Without loss of generality, I'm going to assume that my scores, my beliefs about my scores are distributed uniformly between 0 and 1. This allows me the following perspective on the problem. So since scores are distributed uniformly between 0 and 1, the probability that I get into school 3 is just the probability with which my score is higher than C3, which is 1 minus C3, because the distribution is uniform. That's exactly this segment over here. And what's my expected utility if I only apply to school 3? Well, it's the brown rectangle, right? It's the probability I get in to school 3 times the utility I get from that school. So this is a safety school, gives me a lot of utility and a lot of probability and a small utility. Over there is a rich school. I have a small chance to get in, but I get more utility from attending. Now what happens if I can apply to both? I'm not going to get the sum of the rectangles, because over here I get a really high score, and I get into MIT, and I just go there, but I don't go to school 3. So in fact, what I'm going to get is the coverage of the union of the rectangles. And that's true in general. So finding the optimal size K portfolio is equivalent to finding the maximal coverage by K rectangles. Okay, you don't get to double count rectangles. This is generally, if you allow me to place rectangles anywhere, an NP-hard problem. But this kind of structure can be solved with backward induction or with dynamic programs. So that's polynomial time solvable. OK, so I have a few more minutes. I want to show you a couple of propositions. The first proposition states that if my beliefs are more pessimistic than Richard's, but our preferences are exactly the same, I am going to apply more defensively. He's going to apply more aggressively, in the sense that his first choice is going to be more aggressive than my first choice. His second choice is going to be more aggressive than my second choice, and so on. Why is that? Well, look at what happens if we only get to apply to one school. This illustrates the beliefs of two students. One thinks that his scores are distributed uniformly between 0 and C star, that point over here. The other already knows that he didn't get the first question on the exam right. So his scores must be less than C. Okay? This induces MLRP lower beliefs. What it does is it eats a lot of this first rectangle, but it eats very little from this rectangle. So it makes the safety school relatively more attractive. And this propagates if we apply to more schools, because being rejected by Harvard is not such a bad news. Being rejected from Penn State is worse news. So if your first choice school is less selective, being rejected is worse news. So this propagates further down the list. Okay, this explains this part of the picture. Because when you choose your bottom four schools in your optimal 5-school portfolio, you choose 4 schools conditional on being rejected from this school. When you choose your optimal 4, you don't have this negative information. That's why your bottom 4 are less aggressive than your regular 4. What about outside options? So let's say that Yanai's family is wealthy. We're applying in the same process. We have the same preferences, but he can go to a private school and I can't. I claim that he's going to apply more aggressively than I am. And I have 1 more minute. So maybe I don't have time, and maybe I do, because here's what's happening to Yanai. He's not going to go all the way down to 0. He's only going to go all the way down here. So this eats a lot from his safety school and very little from his rich school. What I can do is take the 45-degree line, transpose this problem, and now we see the same picture that we've seen before, where we have the same coverage problem. We know that in this coverage problem, the optimal portfolio went this way. So in this coverage problem, the optimal portfolio went that way. Okay? It's the same problem, just transposed. So yeah, so this explains exactly this other half of the picture. When you choose your optimal 5 portfolio, you choose 4, and you have the safety of your 5th choice. When you choose your optimal 4, you don't have the safety. So that explains why optimal portfolios expand upwards. And I think I'm out of time, so I'll leave you with this picture once again.